Hi everyone, my name is Aditya K. Kamath, and I'll be presenting iGUARD in GPU Advanced Race Detection. Let me start off with a brief summary of what we'll be covering. We'll start off by talking about advanced GPU synchronization used by emerging GPU use cases, which can cause new bugs when improperly used. We then propose iGUARD, a race detector that uses binary instrumentation. iGUARD performs race detection within the GPU, providing low overhead. It detected 15 previously unreported races in popular open source applications and libraries. Traditionally, computation on GPUs have used bulk synchronous parallelism, such as in matrix multiplication. Nowadays, applications running on the GPU are much more irregular. Applications like encryption and graph processing have more complex needs. They demand semantically richer synchronization to support these needs. In addition, every GPU generation is also getting larger, making global synchronization more expensive. Here, we can see how the trend of NVIDIA GPU sizes in number of concurrent executing threads is constantly increasing. A similar trend exists for AMD GPUs as well. So not only do we need more complex synchronization, but this synchronization should also scale to the growing sizes of GPUs. GPU vendors have responded by introducing advanced synchronization, which we shall now see. The first advancement in synchronization is scoped operations. A scope qualifier, when used with a synchronization operation, specifies a subset of threads for which the synchronization is guaranteed. A warp is the smallest unit of scheduling, consisting of 32 threads executing in SIMT fashion. Many warps make up a thread block, which is a group of threads guaranteed to execute within the same multiprocessor, while many groups of thread blocks make up a grid, which are the threads executing a common GPU kernel. Different scopes can be used to synchronize within these groups of threads. By using a narrower scope, the overhead of the operation is reduced. For example, a device scope fence guarantees visibility for the entire grid, while a block scope fence only guarantees visibility within the thread block, but is 20 times faster than the default device scope on a modern GPU. While scopes can provide performance benefits, they can also be a new source of races. If two threads attempting to communicate through a common memory location use an insufficient scope for synchronization, the synchronization is not guaranteed, causing a race. The next advancement in synchronization that we look at is independent thread scheduling. Conventionally, threads within a warp executed in lockstep with implicit synchronization after every instruction. With ITS, threads now execute independently, removing this implicit synchronization. To understand why ITS is useful, we take an example CUDA code snippet seen on the left, which all the GPU threads execute. Here, two warps are competing to acquire the same set of locks. Assume a subset of both warps manage to acquire their respective locks. The threads which fail to acquire their locks will be stuck waiting for the threads in the other warp to release their locks. Due to lockstep execution, the threads which successfully acquired their locks are forced to wait until the other threads in the warp also successfully acquire their locks. This leads to a deadlock. Instead, with ITS, the threads that successfully acquire their locks can proceed with their execution, removing the deadlock. However, the introduction of ITS can also create races in previously race-free code. This is because the assumption of implicit warp-level synchronization is now broken. Threads within a warp that relied on this synchronization now race with one another. To solve this, new warp-level barriers have been introduced, which should be inserted at appropriate locations to explicitly synchronize these threads and avoid the race. There are other advanced synchronization our paper covers, which we shall not discuss here for brevity. While GPU race detection is not a new topic, we notice that prior work have many limitations. For example, they do not support all the features that modern GPUs have, such as races caused by ITS. While low overhead detectors exist, such as our prior work scored, these require significant new hardware to be introduced. As such, our goals with iGUARD is to provide a comprehensive coverage with lower overheads that does not need recompilation. This detector should be implemented purely in software with no new hardware. We shall now take a look at iGUARD's design philosophy. First, the application, colored in blue, begins execution on the CPU, where all memory and synchronization operations in the GPU kernel are instrumented using in-bit for race detection, colored in red. Binary instrumentation allows us to avoid recompiling the source code. This instrumentation captures the details of scopes used and the threads performing the operations. A key part of our high performance is that the entire process of race detection happens within the GPU. Because of the large number of threads in a GPU, pairwise comparison is infeasible. Instead, for each unit of application data, we keep some metadata that tracks the previous writer and accessor of that data. When performing race detection, this metadata is fetched and used along with the details of the current accessor. The detection logic uses happens before and locks it extended for advanced synchronization. The details of the current access is checked for a race against many conditions. Full details of the different conditions can be found in the paper. The details of races caught are kept in a buffer on the GPU, which is later sent to the CPU. These details are then reported to the user. There are many unique challenges that we encountered. For example, metadata can end up hogging the GPU memory, limiting the size of memory that the application can use. Also, GPUs thrive on parallelism, which the performance of our detector depends on. However, many threads may concurrently access common data, which requires serial accesses to metadata for correctness. In addition, with ITS, individual threads can acquire a lock, or the entire warp can acquire a single lock. We must infer the protocol for locking used by the application kernel. For the details of the solutions that we used, we refer to the audience to our paper. We demonstrate the usefulness of iGUARD by detecting various races that were previously unreported. For example, iGUARD caught 12 new races in the popular open source repositories Gunrock and Lone Star GPU. In addition, it caught 3 races in NVIDIA supported libraries. In total, iGUARD caught 57 races across 21 applications and benchmarks. Not only did it catch a wide set of races, but it also does so at a lower performance overhead. Here, the graph compares the overhead of iGUARD against a previous work, Barracuda. A detailed breakdown of the graph is given in the paper. Across all the applications, iGUARD was faster than Barracuda and on average outperformed by 15x thanks to iGUARD's in-GPU detection. It also did not miss any races caught by Barracuda. On average, iGUARD had a 5.1x runtime overhead. To summarize, concurrency bugs threaten GPU applications. Newly evolving programming features also come with the possibility of new bugs. To combat these bugs, we propose iGUARD, a race detector with low overhead that requires no hardware changes and supports advanced synchronization.